Okay, here we go. All right, so I have the lecture YouTube channel right here under welcome module, and it should say which course it is when you pull that up, the organic chemistry. All right, let's go to here. Wrong one. We got our pages for that. Where here they are. Okay. So we're going to knock out hybridization, and we're going to talk about the different types of structural formulas that we see: condensed formulas, line angle formulas, and discuss isomers. We've already started to talk about polar compounds, what causes them to be polar. We're going to get more into the geometry, particularly right here with hybridization. Okay, so let's jump into that. I've got some helpful images here, so I'm going to pull these up. Where did they go? Helpful images. Here they are. All right. So this is in the resources module. We're going to talk about the different shapes of molecules and hybridization. When you hear hybrid, what do you think about?
Something mixed.
Something mixed. That's exactly correct. That's what hybridization is when two things are mixed together. So if we're talking about chemical hybridization, let me tell you, I just love these markers. I can refill them. It's just great. Hybridization essentially is blending of orbitals to fulfill, how do you spell fulfill? There's an L in there. Fulfill. Now, you asked me to spell DNA polymerase, man, I got you. Fulfill. Is it two L's? Just one. Just one L? That looks so weird, doesn't it? All right, blending of orbitals to fulfill that full set, right? That full set of electrons. So you remember we've got like an octet, the ones in row 3, like phosphorus and sulfur, they can take on 10, as many as 12 electrons. And the reason why the ones in row 3 can do that is they can pull in from the d orbitals for that. Now, with hybridization, when we've got that blending of orbitals to fulfill the full set of electrons, we're mostly looking at that octet, which is that 8 electrons. So all of these non-metals over here, like the carbon, nitrogen, oxygen. So we've got carbon, nitrogen, oxygen. They are all looking to have that full set of 8. So if we go back into the recesses of our brains and we try to remember about the shapes of orbitals and things associated with that, how we label them, we've got S, P, D, and F. These are the types of orbitals. These are the types of orbitals. You got your S orbitals, you got your P orbitals, you got your D orbitals, and you got your F orbitals. F orbitals are through here. To me, they look like space flowers. D orbitals tend to be in our transition metals. We got S orbitals over here as our valence shell. And we got P orbitals over here as our valence shell. So in terms of which orbitals blend, hello, in terms of which orbitals when, it has to do with those valence electrons. So we're looking at valence shells. Those electrons that are on the outside, right? Valence electrons. So s orbitals can only hold 2 electrons. And I'm making these little spaces here. Each one of these can hold 2 electrons, right? And I'm going to draw these as arrows. And just, I could fill in the arrows here for the, so that's 2, 4, 6, 8. This can hold 10 electrons, 14 electrons. This one can hold 6 electrons, right? And this one can hold 2 electrons. Hydrogen can only hold 2 electrons because that's it. Its valence shell is S. It's shaped like a circle, right? P orbitals look like little dumbbells. D orbitals kind of look like, I think they kind of look like hair bows. And F orbitals, or even, yeah, or F orbitals often look like, to me, what I would call space flowers, but they all kind of look different shapes. So, in order to get to that full set of A, if I have elements over here that are in that P block, its valence shell is P, it can only hold 6 electrons. Where am I going to get those other 2? Well, I mean, I could go this route, but like this right here, these are where the d orbitals are. When you're just looking at sheer distance between the 2, that's a bit far, isn't it? This row, though, is just right there next to it, right? This row is pretty close to the d orbitals. This one's not likely to jump a couple levels to get to D, but what is it close to? Probably has an S right there. So if you remember from doing electron configuration, if I were to look at carbon, for example, I'm going to come over on this side. If I wanted to do the electron configuration for a neutral carbon, carbon's atomic number is what? That's 6. So that means it has 6 protons and 6 electrons if it's neutral. So carbon has 6 protons, 6 electrons in a neutral atom. Okay? So if I were to try to figure out where all of those electrons would be, I would have to start at the beginning and move across. So I would go, start here. So carbon's going to have an s orbital. 1s, 2s, 2p. So it's in the second row. Carbon is in the second row in the p block. So let me pull up the periodic table so you can see what I'm talking about, a different visual. You're like, how can I visualize that? Well, we're going to do this. All right. Here's my valence shell is S here. Valence shells are D here. Valence shells are P here. Valence shells are F here. So if I'm looking at carbon, there's carbon. As we're moving across to try to figure out where all these electrons go, carbon is going to start with 1s, it's going to have a 1s shell, because we have to consider each row is an energy level, right? 1s, 2s, 2p. So it's in the second row in P block. That's what this is here, 2p. So I'm using the periodic table to sort out where these electrons are going to be. It's got 6 electrons. S holds 2. S holds 2. And that leaves 2 more for P. So that's where all of those 6 electrons that carbon has. This one are our core electrons. These don't get involved in bonding. So the ones that get involved in bonding are going to be part of those valence electrons. Well, what group is carbon in? You could say 14 or 4A. It's going to have 4 valence electrons, right? But that valence shell is P. So where's it going to get those other 2? Right here. These hybridize, which means they blend together. So these blend together to form the total valence shell. That's what we mean by hybridize. So if I was looking at nitrogen, so nitrogen, we've got 1s, 2s, 2p, but instead of 2p2, it's 2p3. So for nitrogen, these 2 come together to hybridize to form that valence shell. They blend together. How are we doing with that? That might take a minute. Now for the weirdos, like sulfur, sulfur looks a lot, or phosphorus even, if we look at phosphorus, looks a little bit different than nitrogen. But since phosphorus, here's our little energy levels. You see this little section here? Lowest energy level, highest energy level. Phosphorus is real close to that 3D. You see where that is? Phosphorus, their valence electrons are really close to that d orbital. So they can pull in these spaces to blend with P and S. So phosphorus and sulfur, and those that are in that third row, the silicon, phosphorus, and sulfur, it's mostly we see that blending in the d orbitals with phosphorus and sulfur, where you can go to 10, even 12 valence electrons, because they're so close to that d orbital. They have access to that space. We look at carbon. Carbon's way down here. You see what I mean? It couldn't blend with that d orbital on energy levels. So when you're looking at these blocks, think about lower energy, higher energy. That's quite a jump. But not for phosphorus. Phosphorus has already got electrons in that space. You can just kind of pull those spaces in too. So when we're talking about hybridization, in terms of carbon, nitrogen, and oxygen, that's where we mostly focus with organic chemistry. We're talking about blending S and P orbitals together. So for carbon, hydrogen, carbon, nitrogen, and oxygen, we're blending S and P orbitals to make 8 spaces for electrons. Well, 4 spaces. Make if you remember, each one of these holds 2. 2, 4, 6, 8. Make 4 spaces for 8 electrons. Let me get more specific. This P only has 3, right? So we need 4 spaces for 8 electrons. So the different ways that we can do hybridization. Do y'all have any questions about this so far? Are you getting that it's blending? You're taking 2 orbitals, mixing them together? Okay. So the different types of hybridization. Now I've got it going down all the way to D. So if we want to talk about phosphorus and sulfur, we jump into this area. This is where we start blending with those D orbitals. We're mostly going to be worried about right here, this area. So the different ways that we can hybridize orbitals. So I'm going to make another little list here. For carbon, oxygen, nitrogen, hybridization. Come on. Is organic chemistry a con? Well, it puts us together, so you know. All right, so we've got SP, we've got SP2, and we've got SP3. So what is this telling you? What do you think these numbers mean? The number what? We're getting there. What I'm trying to put across, and probably poorly on my part, is that has to do with the number of spaces in that orbital that's blended with the S. Okay? So if P has 3 spaces and S has 1 space, SP means that 2 of these have blended. SP2 means the S orbital and the 2 P orbitals. 2 of the P orbitals have blended. SP3 means all of them have blended. So 1 S orbital plus 1 P orbital wins. Notice all of these are going to have 1 S orbital, right? 1 S orbital plus 2 P orbitals. Well, blend would probably be the same blend. There we go. That's a word. Okay. 1 S orbital plus 3 P orbitals. Blend. So let me put, so 1 S orbital, I'm going to put a little comma there so we don't get confused with energy levels. And 3 P orbitals. Well, how do we know which is which? When is 1 P blending with 1 S, or when are 2 P orbitals blending with 1 S? How do we know? Well, We can look at the shape of the molecules to see, but I kind of take it a step further. I think about it as number of areas with electrons. Number of areas with electrons. So if I have sp orbital, sp hybridization, that means I have two areas where I find electrons. sp, two areas with electrons. sp2, that's three areas with electrons. sp3, four areas with electrons. Because I literally have four orbitals blending together. So if I have four areas of electrons, then I'm going to have four orbitals blending together. If I have three areas with electrons, then I'm going to have three orbitals blending together. If I have two areas with electrons, I have two orbitals blending together. So how does that translate to bonding? Well, if I look at carbon like that, this is going to be sp hybridization. I've got one area here and one area here. Let me get a different color. So that's going to, we're going to start getting cross-eyed. So for an sp hybridization, we can have like carbon dioxide, where we've got a linear molecule. So we've got two areas. Do you see that? In context to the carbon's hybridization, this carbon has an s and a p orbital blending together to meet these bonding needs. So if you're like, I can't wrap my brain around that so well, that's okay. If we were to say, what is the hybridization of this carbon? Look for all the areas where you find electrons. I'm not going to find electrons up here or here, but I am going to find them in these bonds, right? Carbon doesn't have lone pairs or anything like that. So these two areas are where I find electrons. So that's sp hybridization. Okay, so three areas. Well, maybe we have one case where it's something like this. It has a shape like that, where we got a hydrogen, and maybe a double bonded oxygen. Now I have three areas of electrons. 1, 2, 3. So that hybridization is sp2. 1, 2, 3. 1s and 2p orbitals. 1, 2, 3. 1, 2 areas. All right. And then the last one we can consider something along these lines. So how many areas do I find electrons here? 4, right? 1, 2, 3, 4. sp3. How are y'all doing with that? It's okay if it takes a minute. So when I think about it, if I have two areas, this is 1 plus 1 plus 2. This one is 1 plus 2 equals 3. This is 1 plus 3 equals 4. That's another pattern you can look for. I have 3 p orbitals and 1 s orbital. 1 plus 3 is 4. 4 areas. Okay. So, if we were to look at the hybridization of this oxygen, it's got 2 lone pairs, right? So if we were looking at the hybridization of the electrons with that oxygen, it's got 3 areas, so this would be sp2. Okay. Can hydrogen be hybridized? You think? Maybe. Let's see. What kind of orbital does hydrogen have? It's just S, so there's no other orbitals for it to blend with. Yeah, so that's it. No hybridization for hydrogen. It's not allowed. Physics says no. I mean, I guess it could happen, but statistically it would be so small. You'd have a better chance of getting struck by lightning and winning the lottery at the same time. Just doesn't happen. Okay, so you mostly look at hybridization in context to those. Let me see if I can pull up real quickly. There are images on the notes that we can use. Let me pull this up. There we go. Yeah, this is okay. I'm going to enable editing. Let me see if I can find. There's some pretty decent images here that reflect from the book. If you're like, I don't really want to read my book so much, you can look at these images, and that might help. Let's see if I can find. Where is hybridization? It's curved arrows. Molecular geometry. Okay. This is getting into a little bit of that. So let's have a look at this. So when we're talking about molecular geometry, number of groups, you can also consider areas where you find electrons. So if we have 2 groups, it's going to be sp. 3 groups, sp2. 4 groups, sp3. And we assign names for that particular type of geometry. So with 2 areas, we're going to expect it to just be a straight line. So linear. 3 areas, it's going to look like a triangle. So we call that trigonal planar, flat triangle. 4 areas, tetrahedral. So tetra means 4, hedral means it looks like tetrahedral, like a hedron, or tetrahedron. Okay, let's see. Tetrahedral. Let me go to, we can talk about, that. I was trying to find where the other ones were. I don't see it. Okay, so let's talk about the way that we can represent it, and since we got those images here. All right. Any questions on hybridization?
What was the 3 groups?
3 groups are called trigonal planar. So it's like a flat triangle. Plane being flat, trigonal planar. Okay. Okay. All right, here's one. Okay. So this is another way that we can visualize this. If we want to look at it, like the actual bonds rather than straight lines, we can make little bubbles where we would find electrons in those bonds. So this nitrogen, we have 1, 2, 3, 4 areas where we find electrons. We've got that electron pair, and we've got those bonds. So this is sp3 hybridization. Just like with this oxygen, I look for the areas where I find electrons. If there are lone pairs, that counts as an area where you would find an electron. So that's sp3 hybridization. Let me pull up really quickly. I'm going to show you this. We're going to practice hybridization looking at some 3D models. I love this PHET simulations because it allows you to kind of interact with things. Molecule shapes. Where are you at? Here we go. We're going to do hybridization for these things. We're going to use real molecules. All right, so here I got a water molecule. What is the hybridization of that oxygen? What's the first thing we think we should do? What do we base hybridization on? Areas of electrons. So how many areas of electrons are there? 4. I have some in this bond, and I have some in that bond, and lone pairs. So what hybridization is it? sp3. Very good. Let's look at, we already did this one. What about that carbon? What's the hybridization on that carbon? Which one? sp, you're right. We got 2 areas. Look at that molecule geometry, linear. Right? Let's look at NH3. Here's the electron geometry. Let's switch to that. What about that nitrogen? How many areas are you seeing electrons? 4. So what is that hybridization? sp3. Is that coming together a little bit? It's tetrahedral. Let's look at, we could get into the weirdos in row 3, but I don't necessarily want to do that. What about this one? It's 4 areas on that carbon. That's carbon. So what's that hybridization? sp3. There you go.
Oh, just counting.
Exactly. When we move the curtain of scariness out of the way, we're just counting the 4, right? Can you count the 4th? Then you can be an organic. We can use models if we want. So if I went through and I did that, I've got 4 areas of electrons, tetrahedral, sp3. I could remove those lone pairs. What if I had a triple bond here? Let's say that's carbon. Carbon's triple bonded to maybe a nitrogen or something. Single bonded here to that hydrogen. What's the hybridization?
Still sp.
Still sp.
Still just 2, right?
Still just 2 areas. Linear geometry, straight across 2 areas. That all right? like this because you can go with a model set. You can do real molecules versus your own if you want. Just to kind of check, and you can match up with the geometry, so you can kind of pair up that way, and you can also count the areas too. Okay, here we go. So that's hybridization. This is the very wordy explanation. This is count the areas, write out the orbitals. So y'all know the why, and now y'all know the quick way, right? Okay. I couldn't get my brain around hybridization for like a year and a half because nobody explained it to me in a way that I can understand. So I'm like, this is how my brain works. Okay. Now we're going to talk about the how we represent organic molecules with structures. Okay, I'm going to erase this. Did y'all get this? Okay. I try to hit the hard things in class that I know students struggle with. And there's like a lot of work that's got to be done outside of class for learning this. I'm having to talk a lot with Virginian students about how it's like 6 to 9 hours a week outside of class, just doing homework and studying. So I know y'all already feel that. You already do. I had to retake organic too, because I didn't understand that I needed 6 to 9 hours a week outside of class to master the content. I had to retake Chem 2 for the same reason, before I even got to organic, because I didn't realize I had to study 6 to 9 hours outside of class. But, you know, I didn't enjoy it, and that was part of the reason I didn't do so well the first time around. It was really hard. But once I figured out how I learned, and I figured out what I needed to do, that was really helpful. So, organic's difficult, but, you know, if you can get through this and figure out how you learn and what you need to do to master a difficult course, that's going to serve you with all the other courses you got to take beyond this. Because it doesn't get easier. It doesn't. So, and I'm not trying to lie to you or discourage you. Just try to tackle it with the mindset of you just gotta get in there. Do y'all know how to check your answers in the Alex homework? Have y'all played around with the tools on the side? A little bit. Let me show you real quick before I get into this next thing, just in case. I did put a little video on here with screenshots of how to use that. So if I just pick an assignment, and y'all know the videos are just, they're just optional, the video stuff. That's just optional. You don't have to worry about it. I just put those there if you needed extra resources for general chemistry. That's not a required assignment, it's just optional. All right, so I wanted to preview this. I didn't want to do that. Preview, there we go. So I'm just gonna go with one of these. I know this is a lot. So if I was looking at this and I'm like, I don't know what I'm doing. This could give me a step-by-step. If I do the question mark, follow the step-by-step instructions to assign a charge. Or if I'm like, I still don't know what I'm doing, I could have a worked out example that shows me another problem that's similar to it that's worked out. You're like, okay, what does that mean? What is electric charge? Hey, look, all right. So that kind of goes through and breaks up your book into little bits. If you're like, I still don't get it, I'll lose my current attempt. I'm like, I just need to know what the answer is. I'm not getting this. Then this goes through and it tells me how I solve it. Then I can return to the question and try another if I want and still get full credit. So, somebody asked, well, is it a completion grade? If you get through the work, you go through and you get through the work, you keep trying till you get it right, you're gonna get 100. That counts as studying, whether you wanna believe that or not. Sitting here, going through the content, that counts as studying. Studying doesn't have to be, oh, I'm gonna rewrite my notes. That only counts as studying. Or I'm just gonna watch videos. Studying is also doing the homework. So if you're struggling with something, so a lot of, I know it's 60 questions, you're like, Ms. Williams, this is nuts. That's a year's worth of chemistry, okay? That's a year's worth of chemistry to go through on all of this. So this also helps you find where your weaknesses are, and it gives you how to work out each problem so you're able to get through it. I went ahead and extended the due date to the 3rd. You don't need to go back and redo some, just in case. So, and I found out that there were problems over the weekend with the platform. So again, that's another reason why I extended the due date. I'm gonna be fair. This is hard, but I will always be fair. I do want you to be successful, okay? I like teaching, and I want my students to do well. So, okay, so again, yeah, you got all that. It can even take you in the textbook. You click on the little book there. You're like, I need to read about it. Oh, it takes you to the whole thing. What? Page 1? That's not helpful. Oh, wait, I gotta click on that one. Clicked on that. Wait, no, still. All right, so this tells me I gotta go to point 6. I gotta go to point 6. Okay. So y'all understand how to interact with this platform? Okay. That all counts as studying. That's all work that you've done, so you should get credit for that. That's why I count your homework. Okay, let's talk about, we're almost done, I got 4 minutes. All right, I'm just gonna pull this up. We're gonna talk about how we represent the different molecules. We've got, that's bond angles. I'm just gonna write it out. We've got ways to represent molecules. We've got ball and stick. We've got condensed. And we have line formulas, line angle formulas. Structures, we'll say structures, not formulas. Okay. So, I mean, y'all have these images. Let's see what we can pull up on here, because sometimes it's just faster to do this. It isn't typing. Of course. I'm saying right here.
Say the same thing we'd say at kick.
I'm just typing in all of those. Alrighty. Images. Let's gonna pull up images. Alright, so here we go. Pretty decent image there. Kind of like, this will work for now. Open image in new tab. Watch it be tiny. Well, that's not too bad. Well, I mean, it's exactly what you would expect. Ball and stick model, that's like those 3-dimensional models that we were looking at. So we've got carbon in the middle. We got hydrogen, 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 hydrogen. Kind of looks like that. Like the 3-dimensional models. One of our labs that we do is we play around with 3-dimensional models hands-on. So we can spend some time with that. Condensed, if we were looking at propane, CH3, CH2, CH3. So remember the order of the carbons, that tells me this carbon has 3 hydrogens around it, this carbon has 2 hydrogens on it, this carbon has 3 hydrogens on it. That's the condensed. Can also represent it with line angle structures. That's propane. You're like, what? Every end and bend is a carbon. All right? Hydrogens are in 5. So it's understood that this carbon has 3 hydrogens on it, that this carbon has 2 hydrogens on it, and that this carbon has 3 hydrogens on it. So hydrogens are implied. So I could go C, H, 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 C, H, H, C, H, H, H. I could do that. Or I could just go, you see what I mean? So if you're dealing with a molecule that has like 15 carbons on it, or even 10, we'll just do 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons. Every end and bend is a carbon. This one has 3 hydrogens. That one has 3 hydrogens. Every single one of these has 2. You see how I did that? Alrighty, I'm gonna let y'all go. But we knocked that out. We're gonna start on chapter 2 on Thursday. Yes, and this week for the lab, we're doing melting points. Yay! All right, I'm gonna just turn this off.